Returning to our Python code now, we're simply going to rerun some of the tools that we had before, and we're actually going to change things a little bit. So in our first time we had a clip that was 4.43 seconds long. We are going to do a quick little correction here. And I don't usually like replacing my own variables with themselves but smaller, but this is what we want to do here just for the interests of illustration. What we're going to do is take x and make it only the first 4 seconds exactly, which is going to require going up to 4 times our sampling rate plus 1. And so what that's going to do is take our 22,050 times 4 and add 1 thing to the element at the end, because we want 1 more point than we want intervals. And if we just do a quick tweak here, actually we're going to do that right off the bat after we load it so that everything looks right. There we go. Length of 88,201, sampling rate is what it is, and then we do the sound clip is this. We actually should be doing length of x minus 1 over the sampling rate because we're doing intervals, not points, and we get exactly 4 seconds there. All right, so then we can plot our graphs like the time in seconds after the beginning there, and we see again that complicated behavior that we're going to try to decompose into simple frequencies. We won't play it again, though we could if we wanted to. Most importantly, we're now going on to our Fourier transform. Let's actually zoom in on this part here, and to align what we did before on paper with what we're doing here, we're going to call that vector c. These are the coefficients of the Fourier series, and they're all complex numbers. We'll work with that a little bit later. And the challenge that we had was when we plotted these, let's actually just plot the bare bones ones. We had this huge range. In fact, we have now exactly 88,000, where are we here? 88,201 C values left. We can just confirm that. Print the length of those C coefficients, 201. There's going to be some fun math stuff next week about the end here. Let's focus in on this beginning region. We went 0 to say 2000, and we got this, but these were the indices. Flipping back to the paper again, this was plotting indices, k's, against our coefficients, or the magnitude of the coefficients for the absolute value here. Well, that doesn't mean anything to us right now. We want frequencies. Very much like up here, we didn't just plot the x values, we plotted the time against the x values, and that gave us something reasonable. So time against x. So now we're going to build our frequency vector first, and then we can do the rest of it. Our frequency vector, we're going to build that, and we'll call it, say, FR. And remember, it was 0, and then 1 over L, which was 4 now, and 2 over 4, and 3 over 4 units of Hertz. So we actually had a 1/4 Hertz signal, a 2/4 Hertz signal, all the way up to 88,201 over 4. We can do it easily with a range command. We're going to do range of 0 to 88,201, and all of that divided by 4. One little caveat that we need to make this an array before we do that. And let's just make sure that runs. It does. So now we're going to change our plot. Instead of plotting this as the vertical axis, let's go back just to the simple C's here for a moment. So far our plot hasn't changed. We're still going on indices that don't mean anything yet. But now we're going to slide our FR as the x-axis. And now, notice the upper end here, 22,050. That's the highest frequency we can measure. And all the frequencies we're interested in are down here at the bottom end. And using our techniques from, we're going to do this with a new figure. PLT, I'll do a double figure here. All right, so plt.figure. And let's do a fig size just to make it more visible along the horizontal axis. We'll make it 10 by 5. Just get rid of that for a sec, make sure that works. Yep, that works. Then we'll recycle that. And what we're going to do is do a condition here. We're interested in frequencies. This is around the 150 Hertz, 160 Hertz range that we thought things were happening for this particular note. Actually, let's just play it to remind ourselves, because we do have that capability here. There we go. And there it goes again. Our 4-second guitar string. And then what we're going to do after that is see if we can see those frequencies in this chart. And what we're going to do then is we're going to say the, let's call it a condition, is going to be trues and falses, and it's going to be all the frequencies that are less than, let's say, 2000 hertz. So that's going to build a vector of trues and falses. And then what we can do is say, I would like all of the frequencies that satisfy that condition. And then I'd like to take all the coefficients that also match that condition. And because the FR and the C are exactly the same length, this should work wonderfully. And we can see these little peaks here that determine or define the frequency breakdown of our guitar sound. In fact, this is so important, we desperately need to add a label to this, that we're going to do plt.xlabel frequency in hertz. This is something we can understand. There's going to be an oscillation at this many hertz and that many hertz and that many hertz, and we can zoom in if we like. Let's actually zoom in on the 250 range. In fact, let's make a special condition. Let's go from larger than 200, larger than, what's a good range? Larger than 100 up to 250. So larger than 100 and less than 250. In fact, I'm just going to comment out these first ones here because I just want to see this graph here. Fantastic. So there's some major note happening, major amplitude at a certain frequency, at this frequency here of 140-50-ish. In fact, we remind ourselves the frequency for that D was supposed to be 146.83 hertz. Let's get super accurate about this. What we can do is add a line that is vertical. I'm not sure what the AX stands for, but the V line means vertical at x equals 146.83. And there we are. It's not entirely perfect. This sound is decaying over time, which has subtle effects on the frequency, but if you had to name a frequency, 146.83 is pretty much where that peak is happening. Let's just make that a little more empathetic. There we go. So this is the frequency we're supposed to get when we pluck a guitar string at the D that we were trying to get, and this is the decomposition we have. Now what I'm going to do is back this out a little further. Let's go to 1000. And we're going to see that these particular notes that are at higher frequencies, so look at about 300, 4, whatever, these are not random frequencies. These are in fact multiples of that frequency. Look at those peaks lined up perfectly. In fact, you can see the pattern. Let's go 2 more just to capture all the ones that we can see here. 5 and 6. And sure enough, all the multiples, overtones in musical terms of that base frequency, fundamental frequency, that's where we see these other frequencies showing up in the Fourier Transform domain. Take all those off for a second, and you can see now that we have those frequencies represented, but they're not all equally represented, and that's what makes the distinct sound of the guitar versus, say, a clarinet. In fact, we can probably eyeball this. In your homework, you might have to do something a little more sophisticated, but if we just look at these frequencies, so now we are going to build our fake or synthetic guitar. All right, how are we going to do that? Well, we're going to build a new signal called Y, and it is going to be built out of a bunch of sine functions. Now, usually we would build those with the frequency 146.83, but we're going to be using that a lot. So let's take that and just make it a constant, and let's call the base frequency 146.83, and let's call that multiplier in there 2 times, careful, it can't be pi, it has to be n pi, times the base frequency. So this m is exactly replacing all this stuff here. So we could do that calculation right now, just make sure that works. Of course it doesn't. Oh, sine function is also in the numpy library. There we go. Just for the sake of argument here, let's plot t against y just so we can see that. And of course it's not plot, it's plt.plot. That doesn't look very interesting unless we zoom in on the first, say, let's say 1000, see what we see. There we go. So it is a sine function, just a very high frequency relative to the time we're looking at. So it's basically working. Let's go one step further, though. This is just a baseline. We want to match this. We're going to have to worry about scaling, but we'll do that in a second. Let's take a look at these as if they're actual magnitude. So say 5,000. We're going to take 5,000 of that. To get the wrapping working, we're going to need to put brackets around this, just so it knows that it's not done the line yet. Then we're going to have, let's say, 1200 np times sine of m. This is 2 times that frequency, so times 2 times t. And I'm just going to close that bracket and make sure that works. It works like a charm, lovely. And so we're going to keep doing that, the plus at the end there. And using our graph, just to ballpark again, that's about 2500 at the frequency that was 3 times m. And what I notice about the fourth one is that's pretty small. Let's ignore it. It's not going to play a major factor in the sound we're hearing. And then we'll do 2 more. So we'll have the fourth one we're skipping, fifth one, and the sixth one. Or if let's be explicit here, let's have the fourth one, but we'll just have a 0 on it. And just to line things up nicely, we'll do that. So we have the first, or the base frequency, set 2 times that, 3 times that, 4, 5, and 6. The 5's maybe around 400. And the last one is around 600. Just a bracket. And if we plot that, ooh, we start to see a signal that, at least to a first approximation, looks as complicated as, at the very top here, this kind of thing. It's definitely not as complicated. We left some stuff out, but that's a place to start. Now, the only downside, if we just look at scale and think about music and blowing eardrums, this signal went up to 1, and our signal right now goes up to about 6,000. So what we're going to do is just take y and actually let's divide it by its own maximum. That works fine. And then, yeah, now when we plot it, we get a nice range that makes sense for a sound clip. And if we do this right, we should be able to access the same sound clip generation. Right? We're going to do that identically. And then we're going to do the same thing and put in our y. And we're going to see if we actually have a guitar kind of sound. Let's see. Here is the X sound. 4 seconds. Not the same by any means, but not that crazy far away. In fact, let's just dial that down a little bit. Let's dial down by a little more than the max there. So not 1, but like 1.2 times the max. Make sure everything gets recalculated. That seems to take out some of the buzz. And one of the main differences, honestly, is that this one fades over time. We can get a little bit of that by adding a little exponential decay. So we can have our y decay is equal to our y times, let's just do a little exponential decay. I want it to decay about halfway over 4 seconds. That'll give us something like about a 30, or decaying down to about 30% after 4 seconds. Let's try that. And just to see what that looks like, again, np.exponential. Let's plot y decay here. Actually, probably won't see this at the scale we're looking at, but yeah, it doesn't really show much up here. But if we go to our 80,000, which is more of the whole sequence, we'll see that this decays down, looks more like the one we were talking about before. And let's use y decay here instead and play that. When you get to the middle of that sound, it sounds less synthetic than, to me that sounds less synthetic than we might expect. Let's run that. That actually, the later tone there actually sounded more like the guitar. Not perfect by any means, but if we think of what we just put in here, and let's compare 2 things. Here we have a tone generator with 6 tones, 5 tones technically, because one of them is 0, versus spending months building a guitar out of wood and carefully crafting it. And here we can synthesize it to a reasonable approximation with a quick Fourier transform. That is not nothing. That, in fact, gives us a lot of insight into the structure here about how we can decompose waves of sound, waves of signal in electrical fields, a whole host of other disciplines, and achieve an understanding of what's actually underlying what looks complicated. Again, we started with this signal, and we were able to interpret it as this very nice, simple frequency domain interpretation.